Hello, my name is Chengkai Xia, a PhD student in School of Chemical Engineering in SKKU. My supervisor is Professor Zheng Guiqing, and my laboratory is Energy Nanomaterials and Devices Laboratory. Now, I'm one of the big great challengers in 2020 first semesters. Now let me introduce my recent work for about highly activated biochar for multifunctional hydrogen evolution and energy storage derived from Camellia japonica flowers. Biochar is also called as biocarbon. It's one kind of solid residues produced from thermal decomposition of biomass at high temperatures. Usually is from about 300 to 900 degrees without or with a limited oxygen supplies. In recent years, biochar was fully used in water splitting and supercapacitors and some other energy conversion applications. So why we choose camellia flowers? Camellia flowers is one kind of plant which is widely distributed in Eastern Asia. And this kind of plant is rich in heteroatoms such as nitrogen, phosphate, or sulfurs. Withdrawn camellia flowers is usually treated as a garbage and it is not fully utilized. So in our target, we try to synthesize biochar by camellia flowers and apply it on energy conversion and storage. Based on this kind of materials, we try to developing a new strategy to make the full use of biomass. Based on our TGA experiment, it shows that at different degree temperatures, the camellia flowers have different behaviors to be decomposited. Up to 400 degrees, it will be fully decomposited into carbon materials. So we followed our better choosing protocols and generated our nanomaterials like this kind of nanoparticles. In our characterization result, it shows that the sulfur is successfully self-doped into the carbon skeletons, and this kind of materials we marked as SAC, which means that sulfur-doped activated camellias shows a better performance in hydrogen evolution reactions, which means that it will have a better water splitting behaviors comparing to the commercial carbon materials, and it shows that the reason is that our activated materials has higher surface areas, and for other applications. It also shows that our materials has a better performance comparing to commercial carbon materials for supercapacitor applications. The capacitance is much higher than that. So, based on our fully experiment, it shows that. In conclusion, with the self-doping of sulfur elements on carbon skeletons, rapid charge transfer can be provided in electrochemical reactions, which is favorable for supercapacitor and for HER electrode materials. This work provides economical and environmental strategies to utilize waste biomass in cities and gardens, while reducing the production cost of activated carbon-based electrode materials without using fossil fuels.